Okay, so welcome to chapter 12, which is on stoichiometry, the study of lack of emotional response to external stimulus. Let the record reflect that actually got a laugh this year. So, I will not be stoic about that. I will smile because I thought I delivered it better this year. Yeah, some people will call it stoichiometry, some people will call it stoichiometry. Really, what stoichiometry is, it's a long, fancy word. It's a long, fancy word that makes chemists feel smart. Uh, when really you could have just said calculations involving reactions, right? That's what stoichiometry really is. It's calculations involving reactions. Um, and if you're going to do calculations involving reactions, the key is you got to go through what unit? Moles, yeah. Everything's got to go through moles. So the idea behind stoichiometry is mass is conserved in chemical reactions. You're not going to gain or lose any mass. You're going to start with start and end with the same atoms. When you look at a balanced chemical equation, that'll tell you the ratios of things in the reaction. And if you want to do calculations involving the reaction, you got to go through moles. So not everyone's familiar with these ads, but if you've ever heard a gotta go to moles ad, that's what I think of when I'm doing stoichiometry. Gotta go to moles. And if you haven't heard a gotta go to Modell's ad before, then you're probably lucky. At any rate, the first step is figuring out how to convert different things into moles. We've touched on this in the past. So now I want you to think for a moment. How do you get to moles from mass? How do you get to moles if you have density and volume? How do you get to moles if you have volume and concentration of a solution? How do you get to moles from number of particles? How do you get to moles from pressure, volume, and temperature of a gas? So take a moment, think about each one of those things, and then share with your neighbors. Okay, if you know the mass of something, Kat, tell me how to get to moles. Wait, no, not gas. If you know the mass of something. So what units do we measure mass in? Grams, all right? So you have grams. If you want to get to moles, you need to multiply by a conversion factor that has what on the bottom? Grams, and on the top, moles. And so that conversion factor is going to be 1 mole for every molar mass of grams. So essentially, you're dividing by the molar mass. What if I know the density and the volume of a liquid? So sometimes you have a liquid, you know its density, you measure it out by volume. Sophia, what could you do with density and volume? Or can you tell me what units density would be in? All right, this would be in grams per liter, or for liquids, usually it's going to be grams per milliliter, but it could be grams per liter. All right, so if you know the density, which is in grams per milliliter, volume, what units do you think you would measure that in, Maddie? Could be liters, or in this case, probably milliliters. If I take grams per milliliter times milliliters, that's going to give me grams. So if you take density times volume, it'll give you mass. And then once I know the mass, how can I get from the mass to the number of moles? Well, divide by the molar mass. So use density and volume to find mass, and then divide by the molar mass. All right. So what was the next one I asked? All right, what if you have volume and concentration of a solution? All right, volume and concentration of a solution. Volume or concentration is going to be in what units, Anna? Moles per liter. So concentration will be moles per liter. All right. So then volume you would want to measure in what units there, Matt? Liters. So if I take volume and concentration, how am I going to get to moles? Just multiply them together, all right? So concentration times volume would equal moles. All right, if you know the number of particles, like there are 3.7 times 10 to the 20th molecules in this sample, there you're going to use what? Avogadro's number. That's the least useful one because we're never actually measuring the number of particles. Usually we're doing this in reverse. You might get a question that asks like how many actual molecules are there in a sample. And then you go through the number of moles to get the number of particles. But the number of particles is not that useful a number other than to tell us, oh wow, there's a lot of particles in any measurable sample of matter. So that's the least useful one, but still one you're expected to be able to do. And then we have gases, all right? And I want to make a clear distinction here. The most common mistake I see in stoichiometry problems is people treating a gas like it's a solution or treating a solution like it's a gas. So saying if you have 3 liters of a solution and then they use that 3 liters in the ideal gas law, it makes no sense because it's not a gas. Or using, if they have volume of a gas and then they say, well, I don't know the molarity, so I can't figure out the number of moles. Well, that's for a solution, not for a gas. So you want to make sure you keep gases and solutions separate in your mind. But if you know pressure, volume, and temperature of a gas, what can you do with those 3 things? Derek? Use PV equals nRT. So number of moles is going to equal PV divided by RT. Pretty straightforward. The The only things you have to worry about there, remember, temperature has to be in what units? Temperature's got to be in kelvins, and then you have different choices for R. So you want to make sure that you choose the R value where the pressure units match the pressure that you're given. All right, and then something that's bothered me for years is this thing called STP. All right, so what does STP stand for? Besides Stone Temple Pilots. And what's funny is people are like, who? They were a 90s grunge band. Standard temperature and pressure. All right. So the student question is, what about SATP? Because in honors chem, you were required to memorize a distinction between the two, and I will say this about that. Number one, SATP I never heard about in my life until I started working in this building, and it's one of those things that was part of the curriculum here. Number two, I hate STP for reasons I'll elaborate on in a moment. So I definitely don't want to introduce another similar thing and make you know both of those things. All right, so here's the good news about STP. You may have been required to memorize a number associated with STP before. Okay, who can spout the number off for me, Nick? 22.4, all right? So here's the problem I have with that. People memorize this number, 22.4, and just think of it as like, well, it's just a magic number, all right? Standard temperature and pressure is defined as this. It's defined as temperature of 0 degrees Celsius and a pressure of 1 atmosphere. All right, that definition is actually on your formula sheet. All right. Now, here's one of the problems I have with STP. Does anyone feel like doing their experiments at 0 degrees Celsius? You want to go outside today and do your experiments out there? No, it's cold. All right. There's no point in defining a standard that no one would actually want to do in the lab. All right. The second thing, like I said, is it encourages you to memorize a number. And that number is 22.4. Well, where does 22.4 come from? Well, 22.4 comes from the ideal gas law. If you decide what's the volume, you can say V equals nRT over P. And if I plug in 1 mole and I plug in the value for R in atmospheres, which is 0.0821 liter atmospheres per mole Kelvin, and I plug in temperature of 0 degrees Celsius, which is 273 Kelvin. Again, not a number you need to memorize because it's on your formula sheet. And I divide by 1 atmosphere pressure. First, I'll notice that moles will cancel, Kelvin will cancel, atmospheres will cancel. I'll be left with liters. And the volume I get is Does anyone want to confirm it on their calculator? It's 22.4. So there's no reason for us to memorize this number when it's just a specific case of any gas under ideal conditions. So what I would say is don't even bother worrying about STP. Anytime you have a gas under any conditions, just use the ideal gas law to solve for the number of moles. The only reason I find this helpful is if you raise the temperature to about room temperature and you do the same calculation, you find that a mole of gas occupies somewhere around 25 liters. So for estimating purposes, whenever I'm trying to estimate whether an answer makes sense, if it's somewhere around normal conditions, I think, all right, a mole of gas should be about 25 liters. But that's the only place where it's really useful. I wouldn't spend any time on this, and don't worry about SATP. There are no problems on any test we would give you where you need to know the number 22.4. There's no problems on the new AP test where you need to know the number 22.4. All right, so you can erase it from your memory if you so choose. And if it was never in your memory, consider yourself lucky. All right, so we have all these different ways to go to moles. So the next question is, what do I do with moles once I get there? Well, moles allow us to use that balanced chemical equation, the ratio from the balanced chemical equation, to go from moles of one thing to moles of another. So typical stoichiometry problems. Essentially, the rest of this lecture is all problem solving. So a typical stoichiometry problem is, given the amount of one substance in a reaction, find the amount of another substance. So in general, these kinds of problems are going to have 3 steps. First, you're going to take your given quantity into moles. Next, you're going to take moles of that given substance to moles of the substance you're asked about. And that step is where you're going to use the ratio from the balanced chemical equation. And then the last thing you're going to do is take that number of moles and convert it to whatever quantity was asked for. So by that I mean you might be asked for grams, or you might be asked for liters, or you might be asked for concentration. So there's different things you could be asked for. So go ahead and solve this first stoichiometry problem. All right. Let's solve this first one. All right. So in the first problem, what is the given quantity? The given quantity is a little hidden here. But what is the amount of stuff that we're given? Okay. 1 kilogram of aluminum. So it says for every kilogram of aluminum, this is really my given quantity. And there's no number actually given because it's just 1. All right, so I'm given 1 kilogram of aluminum. And I'm asked for what quantity am I asked to come up with? Sophia? Mass of ammonium perchlorate. Ammonium perchlorate. What do you think ammonium perchlorate is in the equation? The NH4ClO4. All right. So we're asked for mass of NH4ClO4. And so one question that came up was, well, do you want grams or kilograms for mass? And the answer is, if you're not given a specific unit, you can answer in either one. Right? If I ask for a mass and you answer in kilograms, or you answer in picograms, or you answer in yottagrams, that is actually a thing. If you look at all the metric prefixes, they actually go like to really big and really, really small. And I think maybe the smallest one is zepto. There's like yotta and zepto or something down at the bottom. I don't know. Yeah, I think those names probably were fun to make up. The smallest I've ever heard actually used is femto, which is 10 to the negative 15th, I think. People talk about doing things on a femtosecond scale. So 10 to the negative 15th seconds. Really, really short time periods. At any rate, the point is we're asked for mass of ammonium perchlorate. We could give it in grams. We could give it in kilograms. So I'm gonna work through the whole problem and give it in kilograms, and then I'll show a shorter way to do it. But I'm going to start by taking my given quantity, 1 kilogram of aluminum. Step 1, gotta go to moles. How do I get there? Molar mass. All right. So there's 1 mole of aluminum for every 27 grams of aluminum. Oh, wait a minute. So you might be saying to yourself, I have kilograms, the molar mass is in grams. So you might say to yourself, all right, hold on. First thing I'm going to do is put the mass in grams. So there's 1,000 grams in 1 kilogram. And then you could say there's 1 mole for every 27 grams of aluminum. I want to point out that when I solve these problems, I always write the substance along with the unit. That's important. That's going to help me keep track of things. When students start to struggle with these problems, almost without fail, I ask them to show me their work, and I see a bunch of numbers jotted down, some with units, some without, and the ones with units don't say what substance they refer to. If you want to keep track of this and not make mistakes when you're dealing with more complicated problems, develop good habits. Start by writing all your units out and including the substance with each unit. So instead of just writing 1 kilogram, say 1 kilogram aluminum. All right, so far I've done step 1. I went to moles. Kilograms canceled, grams canceled. I have moles of aluminum. Now, once I have moles, I'm going to move on to step 2. Step 2 was use the balanced chemical equation to go from moles of one thing to moles of the other. So given that I'm asked about NH4Cl04, my next conversion factor is going to have moles of NH4Cl04 on top. And on bottom, it's going to have moles of aluminum. What numbers go into that ratio? All right, 1 to 1. If I go back to the equation, it's 3 to 3. You can mentally change that to 1 to 1 if you want. I usually just copy them directly from the equation. I heard Kaya saying she likes to do that. So some of you may feel more comfortable just copying them directly from the equation and then reducing. Some of you may reduce in your head. But I would write 3 to 3. All right, so I've done step 2. The last step is go to the quantity asked for. I'm asked for mass of NH4Cl04. So how do I get from moles to mass? Well, to get from mass to moles, I used the molar mass of aluminum. To get from moles of ammonium perchlorate to grams of ammonium perchlorate, I'm again going to use the molar mass, this time the molar mass of ammonium perchlorate. So I'm going to have 1 mole of NH4Cl04 on the bottom. And what's the mass of 1 mole of ammonium perchlorate? All right, I'm hearing different numbers. 117.48. All right. And now I'm going to take the final step of converting this back into kilograms and saying, all right, there's 1 kilogram for every 1,000 grams. So if I go through and follow out my units, moles of aluminum canceled out, moles of ammonium perchlorate canceled out, grams, I'm going to be left with kilograms of ammonium perchlorate. And how many kilograms was it? I'm counting on you guys. 4.35 kilograms of ammonium perchlorate. All right, I want to point out something that I'm hearing in the room. I'm hearing people say, oh, 4.352, 4.354. Little arguments going back and forth about what's going on in that third decimal place. I want to remind you, there's always uncertainty in that last digit. When you're doing corrections to problem sets and your answer, agrees with mine in the first 2 digits and disagrees in the third digit, I don't want you to spend time worrying about that. There's always uncertainty there. So as long as you follow the right process, that's what I care about. And I don't want you worrying about those last couple digits. So notice what we could have done here. We could have skipped the step where we converted kilograms to grams, and then the step where we converted grams back to kilograms, because they just canceled each other out. So these 2 steps really weren't necessary. And it also would have been fine if you reported your answer as 4,350 grams of ammonium perchlorate. All right, questions about that process? Sam does not have questions about the process. All right. So then next example. I know a lot of people were working on it while I was going over the first one, which is fine. Do you need a little more time? All right, take a few minutes, do the second example. All right, let's do this example and then we'll call it a day. So what's my given quantity here? What's my given quantity? The liters and the molarity of a solution. So I have two given quantities. All right. And what am I asked to find? I'm asked to find volume. Volume of hydrogen gas. All right. What sets this apart from the last one? Well, a couple of things. Last one only involved masses. And last time we were given a chemical equation. This time we're not. So we're going to need to generate a chemical equation at some point, and then we can do our 3 steps. So chemical equation, we were told magnesium reacts with HCl, and it makes hydrogen gas and magnesium chloride. So I'm going to want to balance that. Looks like if I put a 2 here, everything will work out. So I have a balanced chemical equation. Then I'm going to write down my given quantities. My given quantities were a volume, what was it, 2.25 liters? And I was told that it was 12 moles per liter HCl. So 12 moles of HCl per 1 liter. If I multiply those two together, I'm going to get to moles of HCl. Step 2, take moles of HCl and turn it into moles of hydrogen gas. All right. What numbers are going to go into that ratio? Sungwon? 1 mole of H2 for every 2 moles of HCl. All right. Now I'm gonna stop my calculation there and calculate the number of moles, because that's next. I'm gonna have to use PV equals nRT to get the volume. So right there I can calculate the number of moles, and how many moles of H2 do I make? 13.5. Does that sound about right? Yeah, sounds about right to me. So then PV equals nRT. Oops. V is going to be nRT over P. So that's going to be 13.5 moles. 0.0821 liter atmospheres per mole Kelvin. Temperature, what was the temperature that was given? 22 degrees Celsius, so 295 kelvins. And the pressure was 1.07 atmospheres. All right. Giving me in the end a volume of 305 liters. All right. So that's our basic process for stoichiometry. Tomorrow we'll do one more simple example like this. We'll talk about what a limiting reactant is. We'll talk about percent yield, and then we're done with the basics of stoichiometry.